Okay guys, I'm back with another video related to complex number, and in this video I'll explain the problem with polar coordinate system, because I know some of you might have some doubts like why we kept r positive and theta to be between minus pi and pi when we converted complex number in the Cartesian plane to complex number in the polar coordinate system. Okay, the first thing I want to convince you is whenever we plot complex number in the Cartesian plane, we call that plane Argan Plane. And I hope you remember, whenever I get a complex number x plus iy, I just convert it into the coordinate x comma y, and I'll use the x-axis, y-axis and plot the point. Okay, that's it. But whenever we plot a complex number, we take the x-axis to be the real axis, because we are plotting the real part of the complex number in the x-axis. And then we call the y-axis to be the imaginary axis, because we are plotting the imaginary part. Okay, now we convert this Cartesian form into polar form, and I explained in my previous videos we call that form the modulus argument form. Okay, so there is one problem with the polar form or the modulus argument form, and the question is, why did we keep r positive and why did we keep theta to be between minus pi and pi? Okay, I'll try to answer best for those questions now. Okay, so let's start. So look at this. In the Cartesian coordinate system, every point will have a unique representation. For example, we can focus on this point. What will be the coordinate of this point, or how do you give that point a coordinate? What we do is we take this length, let's say it's like 1 2 3, let's say approximately 5 units and 4 units, maybe this will be called 5 comma 4. Likewise, this is another point, and this point will have another representation, and since we are moving in the negative direction along the x-axis, this point will be something like, let's say, minus 1 comma maybe 3, and this one will be like x will be negative and y will be negative, etc, etc. So my point is, every point in the Argan plane or the Cartesian coordinate plane will have a unique representation. You know the word unique. So every point will have a unique one and only one representation. Okay, now let's focus on the polar coordinate system. Okay, let's have a boundary here. Yeah, okay. So what do you call this point? I hope you still remember the polar system. And what do you call this point? Yeah, we call this point the pole. So what do you call it? Pole. And what's this red line? Yeah, you're right, initial line. Okay, so I wanted to focus on this dot, and let's say it's like 1 2 3, let's say 3 units from the pole, and the line, this line, initial line, is supposed to be 0 degree. The reference is 0 degree. So the coordinate of this point is 3 comma 0 degree. Okay, now remember, we always measure the angle starting from the initial line. Okay, let's say this is also 3 centimeters or 3 units or whatever. So this coordinate will be 3 comma, so what's the angle if I start from here? Yeah, that will be 90 degree, or let's say pi by 2. By the way, let's assume this is like 1, 2, 3, 4, 5. And what is this angle? What is this much? We should always start measuring from the red line, the initial line. So this is 180 degree. So this coordinate will be 5 comma pi. Okay. I want you to focus on this. So look at this. I have the initial line, and the arrowhead is the positive part. So remember, this arrow is the positive part. So if I turn, let's say 45 degrees, the picture will be something like this. So this is the positive part or the positive direction. If I turn it, let's say 120 degrees or 130 degrees, it looks something like this. Yeah. So look at this. Corresponding to every angle, we have a positive walk. If I walk in this direction towards the arrow, we will call it positive. Now let's say I turn 30 degrees or 45 degrees, something like this. So if I walk in this direction towards the arrow, I will call it a positive walk. We are walking in the positive direction. And now I turn approximately 120, 130 degrees. So the positive walk will be, this. So why I am telling you these things is because when you reach 90 degrees, the positive walk will be, look at this, when we reach 90 degrees, this will be our positive walk. That means if you go up, then R will be positive. And in 180 degree, this will be the positive walk. Isn't it? When you turn 180 degrees, the picture becomes something like this. And when you turn 270 degrees, oh my, this will be the positive walk. That means going downwards will be called positive. Remember, this is not the Cartesian coordinate system. It's an entirely different system called the polar coordinate system. Don't get yourself confused with Cartesian coordinate system. I know in the Cartesian coordinate system, this is the negative y-axis and this is the negative x-axis. But things are not the same in the polar coordinate system. Okay, so let's erase a few of these things so that we get a clear picture. So now look at this. I want you to plot 2 points, 3, 0 degree and 3, pi. So 0 degree means the direction of the red line. So 3, 0 means it will be this point. So I'm going to mark this as 3, 0 degree. Now it's 180 degree. So I have to start from here and move 180 degrees, and it is positive 3. And positive means it will turn like a clock, and this is positive. And it will be somewhere around here. So this is my 3, pi. Now what about minus 3, pi? Okay, so the angle is 180 degrees. So I turn the same amount, but it is minus 3. If I walk in this direction, it's positive. That means I have to walk in the negative direction corresponding to 180 degree. And that will be minus 1, minus 2, minus 3. Okay, so this is the same as minus 3, pi. So my point is, in the polar coordinate system, the points do not have a unique representation. So I hope it explains everything. Now let's start with the Argan plane. Let's start with the Argan plane. Argan plane means we convert complex numbers into Cartesian coordinates, and we consider the x-axis to be the real axis and y-axis to be the imaginary axis. And we plot the points or the complex numbers as if they are points on the Cartesian coordinate system. And the good news is every complex number will be associated with a unique point in the graph. That means every point will have, or every complex number will have, a unique representation. Now when we convert the complex number into the polar coordinate system, I hope you remember in the last video I taught you how to convert complex numbers from Cartesian system into the polar coordinate system. Okay, and in that video I asked you to keep r positive and theta between minus pi and pi. Okay, and the reason is in polar coordinate system the points are not having a unique representation. The points do not have a unique representation. And this is the best example. You can try other examples by yourself later. Anyway, every complex number must have a unique representation. So what we do is we do two things. One is we make sure r is always kept positive. Do you remember the formula for r? Yeah, root under x square plus y square. And you know very well when we take square root we go for plus or minus, but you should keep only the positive value. And the next thing, for the points or for the complex number which lies in the first quadrant or the second quadrant in the Cartesian system, we make sure the angle stays between 0 to 180. So for those complex number which lies in the first quadrant and in the second quadrant, we make sure the angle lies between 0 to 180. And for those numbers which are in the fourth quadrant and in the third quadrant, we make sure the angle lies between 0 to minus 180. So I hope now you know why we keep r positive and theta between minus pi to pi. Okay.